Hello everyone, this is going to be another statics video covering frames and machines. We're on chapter 6 and this is going to be example number 101 from the statics book by Hippler. Okay, so this question asks us, it states that if a clamping force of 300 newtons is required at A, determine the amount of force F that must be applied to the handle of the toggle clamp. So we're trying to find the force F right here, right up here. Okay. So to begin with this problem, I like to. So we're gonna have to analyze one body at a time. So the big question is, which body are we gonna analyze first? So we have a couple options here. Since we're trying to solve for F, it wouldn't be convenient to solve for the body CBF here. So let me draw that out. C, this B. So it wouldn't really be convenient to look at this body first because we don't know force F, we don't know forces at C, and we also don't know forces at B. So that would be potentially 2, 4, 5. That would potentially be 5 unknowns, and we only have 3 equations. So that wouldn't help us in any way. So we're going to have to pick another body. So we could look at BE, but that's just a simple body. It doesn't really help us either. But here, they give us a force of 300 newtons at A. So they're giving us a value here at A. So since we have a value for A, let's look at a body that involves A, which in this case would be ACD. So we could go ahead and start there. Okay, so at A, we're going to have a force of 300 newtons. This is a clamping force, so it's going to be a reaction from the ground on the body, just upward. Okay, and then at C, it's a pin here, so that means we're going to have pin reactions. CY, CX. And again, it doesn't matter which direction you assume for the reactions because your final answer will let you know if your assumption was correct. And before I forget, it's our coordinate system right there. And then finally at D, there's a pin there. So I like to just assume positive for my pins. It just makes it easier to keep track of at the end. So that's fine, we can just assume that then. Okay, so now from here, let's also establish a convention for the moments. So we're going to say a counterclockwise twist is going to be positive. Clockwise is going to be negative. Okay, so now okay, so from here, eventually we're going to want to find force F. And we know force F is connected on the body CBF here that we drew earlier. That body CBF, what does it have in common with our body here? Well, the pin at C. The pin at C connects both those two bodies. So what we want to do here is we want to find one or both of the forces at C in order to go in and solve for F later on. So because of that, that means our moment equation cannot be at C, since if we take the moment at C, we're eliminating those forces, and that would not help us. So we can either take the moment at A or D. In this case, it'd be smarter to take it at D to get rid of these two unknowns. So that way you're only two unknowns, and that moment equation is Cx and Cy. So let's go ahead and do that. Sum of the moments equals 0 at D. Okay, so we have a force at 300 newtons, and at D it's going to cause a negative moment because it's going clockwise. So negative 300 newtons times 0.235 meters. 235 is the distance here, as seen from the picture. Okay, and now our other force here that's going to cause a moment is Cx, and that's going to want to twist it in the same clockwise direction as the previous force, which means this one's also going to be negative. So negative Cx times 0.06 meters, and 0.06 is this distance here. Let me just keep it consistent. Okay, and all that equal to 0. And now Cy is not going to cause a moment because Cy is along the line of D, so there's no moment arm here. So now that means we can solve for Cx. And if we do so, let's simplify this a little bit. So 300 times 300 newtons times 0.235 meters is negative 70.5 Newton meters minus Cx, 0.06 meters. Let's put that on the other side actually. Okay, and now if we solve for Cx, we're left with 70.5 divided by 0.06. We're left with negative 1175 newtons. Okay, so that's our Cx there. Okay. Now moving on. So we have a Cx here. We could do some of the forces in the x direction. If we did that, we would just get Cx equals negative dx. And if we tried to do some of the force in the y direction, as you can see here, we know A in the y direction is 300. We don't know Cy and we don't know dy, so we wouldn't be able to solve for any of the two, Cy or dy. So then our job here is pretty much done for this body. We can now move on to CBF and see if we're able to solve for any of those forces. So let's go ahead and do that. Okay, so moving on here. Okay, now let's look at that body CBF that we mentioned before. Let me draw that. C and B. Okay, so they're telling us, let me just draw this angle in here. They're telling us that's 30 degrees, and then they're telling us that the force here, we're going to assume that's 90 degrees. So then if we try to find the force in the x and y components, so this is that line there, it's 30 degrees, and let's say this is our x-axis, this is our y-axis, so we know this is 90. That means this is 30. If this is 30, this is 30, right? Which means this here is 60. So we're left with So this is 60 degrees. Okay, now let's draw in our reaction forces. So C, at point C here, that is the same pin that we drew on beam ACD from before. So because this is the same pin, but it's a different body, Newton's third law should hold for these reaction forces, meaning that the force Cy will be equal and opposite as well as Cx. So previously we had our Cy going up and our Cx going to the right, but now it's going to be equal and opposite. So Cy, Cx. And then B here, B is also a pin, but we can say that B is also a two-force member since the beam BE here is a body with two pins on both sides. This is B and this is E. So then this is one body with a pin on each end. We can resolve that as just a simple two-force member here. Let's call that BE. Okay. So now, from here we can do some of the forces and some of the moments. So let's go ahead and start with some of the forces. So some of the forces in the x direction equals 0. We get negative. So let me draw this from before. So let's copy this. Oh, sorry. Let's just write it down here. Okay, so in the x direction, we have Cx going in the negative direction. So that means it's going to be negative, and then the value of Cx, which is negative 1175 newtons. Okay, and now we also have F. The component of F in the x direction here is going to be positive since it's going to the right. F, and that component is going to be this horizontal, which is cosine 60. And then finally we have BE here. Now they also give us this dimension, so let's draw that in there. It's 30 degrees. And then BE, the x component of BE is going to be going to the left, so that's going to be negative. And it's going to be BE, and that component is going to be cosine, so this end. Or I'm sorry, I apologize, sine, this opposite end here of 30. And that's going to equal 0. So we could simplify this out a little more. So it's going to be F cosine 60. So this is a positive, but when we move it to the right, it's a negative. And actually, cosine of 60 and sine of 30 are both equal to 1/2. So we can even simplify this further. Okay, and we can also multiply each term, or I'm sorry, divide each term by 0.5 to get rid of these coefficients. So let's do that. So if we divide everything by 0.5, so we're left with, for equation 1, we're left with F minus BE equals negative 350. So that's equation 1. Okay. And now we can also do some of the moments. So let's do that. And again, we can do it, we can take it about any point that is not point F, since we're trying to solve for F. But if you can see here from equation 1, we have F and BE in the same equation. So we can, if we choose our point at which we're taking the moment about conveniently, we can do it so that we just have two equations and two unknowns at the end here. So we need this final moment equation to have both F and BE in it somewhere. So in order to do that, we can take the moment about C to include both BE and F forces. So let's go ahead and do that. So we will get, so taking the moment at C, we get the contribution of BE. So we have in the x direction, so BE in the x direction is going to be, it's going to cause a negative moment, and it's going to be PE sine 30. And that's all going to be multiplied by that distance, which is 0.03. So you can see it right here, this distance here. And then BE's vertical component is also going to contribute to the moment. And that's going to be positive because it's going counterclockwise, and it's going to be BE cosine 30. Times the distance, which is 0.07 meters. And then F is also going to have contributions for the for its x component, which is going to be minus F cosine 60. Times the distance is going to be, so they're telling us this is 275 here from B to F, the vertical distance from there. So if we drew a triangle out here real quick, we know this is 30 because they tell us here. So this is simply 275 cosine 30. Okay, so then that means our distance, our moment arm there is just going to be 275 sine 30. But we're writing this in meters, so it's going to be 0.275 sine of 30. Okay, and then we have one more contribution from F, and that's going to be the vertical component. It's going to be acting downward. It's going to want to cause a negative moment. So it's going to be negative F sine 60. And then the distance there is going to be, so the horizontal distance from C to F is going to be 275 cosine 30. That's from B to F, plus from B to C, which is 70 millimeters. So 0.275 cosine 30 plus 0.07. And then all that is equal to 0. Okay, so now if we simplify this out even further, we can get negative BE times 0.015 BE .0606 217 minus F .06875 minus F 0.33562 7, all that equal to 0. So now simplifying even further, combining the coefficients we get for equation 2, we get BE times 0.045 62 minus F times 0.335 6217, and all that's equal to 0. So now that's our equation 2. So now we have two equations, two unknowns with our equations 1 and 2. So with that, now we should be able to solve pretty easily. Okay, so let's go ahead and solve that. So let's substitute equation 1. Let's solve for BE. So additional step here. So we have F plus 2350 equals BE. Okay, and we're going to substitute that into equation 2. Okay, when we do that, we get, so BE is now F plus 2350 times 0.04562 minus F times 0.335 6217, all equal to 0. Okay, and then foiling this out, we get 0.04562 times F plus 107.207 minus F times 0.335 6217. Okay, now combining our F's, we're going to combine the F's and then move them to the other side. So we get 107.207 equals positive 0.2900 times F, and then when we solve for F, we get that force F is 369.679, which is approximately equal to 370 newtons. And that right there is your final answer.